you start to see like some application of what we're doing here for sure. Now, lots of what I'm giving you, you guys have to remember, like it doesn't feel like it because we are definitely the elite mathematicians of Elkin High School right now. So it feels like we're at pretty high level. But in the grand scheme of mathematics, we are Calc 1, which when you go to college might be taught by like grad students. The mathematics professors at big schools feel like Calc 1 is a nothing class. You know, that's just like a stepping stone. So we're starting to see where this can apply. These are going to be situations that are still a little bit like simplified from the real world. So you're going to be given like parameters that you're not having to figure out on your own, and in the real world you would have to do a lot more. But it at least gives us like a window into like where this could be applied for this. So, for example, when a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, what dimensions will produce a box with maximum volume? So, so for this, you're supposed to do a little bit of this in Math 3, these like optimization problems, but obviously you're not doing the calculus that goes with it. You're using Desmos for everything. But even that, at least in Math 3 have not done any this difficult. You may have done the ones where you cut the corners out of a box and you fold it up, and you have to do that. I did those with my Math 3 this time. This is a little bit like that, but it's got a little more complex part for it. Now certainly like they're giving you parameters that you know. That would be figured out ahead of time. But you can kind of see like if you are working in a manufacturing facility that produces packaging for different products, there's got to be someone somewhere that works on like the design of the packaging. You certainly would be concerned with the volume of the box because it needs to be a certain size. And then you would also be concerned with something like surface area because that tells you how much material you're using for your box. You could go into a lot more with this, with like what your machinery is made to do and what's going to be most economical, like what shape. Also, you're also throwing marketing in there in the real world because a lot of times, they make the cereal boxes bigger, but they don't actually put any more cereal in them. They're just trying to make you think it's more than it is. If you ever find anything that's like in a cone-shaped package, it's a scam. Because anybody remember the volume of a cone formula? It's not the same as a square. Same as sort of same as a pyramid. Like your volume formula for a cone is 1/3 of a cylinder. So like if you have a cylinder that's the same height and radius as a cone, that cone's only like 1/3 of the third of the volume, but it looks almost as big sitting on the shelf. So that I think is a scam every time I see anything that's in like that type of packaging. So it does not have as much in it as you think it might would. There's lots of things that go into this, but certainly this would be a piece that you would consider here. So we need, first of all, to think about this open box. This open box means it does not have a top. It has a square base and a surface area of 108 square inches. So let's draw us our box over here. The base is a square, and then I've drawn this badly. Hold on. Let me start it. Let's do like this. Our base is going to be square. The height is not a cube. It doesn't tell us it's a cube. It tells us the base is a square. So like we know this side and this side are the same. We do not know how high it is. It could could be a cube, but it might not be. So we've got to figure out what the dimensions of this are going to be. So I need to think about, it tells me basically what you're going to be doing with most of these equations is you're going to be setting up two separate equations and then substituting in one for the other. Now, what we're looking for is maximum volume. So certainly, I'm going to have a formula for volume. Okay? And that is the one that I'm going to be taking the derivative of. Take the derivative of this. Okay? Because I want to find the maximum of volume. So to find maximums, I take the derivative, I find my critical points, I do first derivative test or second derivative test if you'd rather, to find the maximum. So volume is the formula that I need to be taking the derivative of. However, the volume of this is very simple, right? It is x times h, or if I want, I can write it as x squared times h, right? Volume is just length times width times height. It's a very simple formula, but it is not a simple derivative because you have an x squared and an h, and thus far we do not know how to take a derivative of anything with like those two separate variables right there. We are going to do something with related rates, but this is not a related rates problem. So we have an issue because we have three variables right there. And we need it down to two variables. We need this to all be in terms of x or all be in terms of h in order for us to do this problem. So right now we can't do anything. What we're going to have to do is we're going to take our other piece of information they give us. And the other piece of the information is that surface area is 108 square inches. So we need to write an equation for surface area. And they're not going to give you the equation for surface area for this. You have to think about it. So, the surface area is the area of all the faces added together, right? So, like, for example, what is the area of the base? X times x, so x squared. And I would say there's one on top and bottom, but what did they tell us about this box? It is an open box. Does it have a top? It does not. So if it did not say open box, we'd have 2x squared because we'd have one on top and bottom. But they tell us that this is open, so we are just going to do x squared. Then I need to find the area of, let's say, like the side piece. What is the area of this right-hand side? X times h. What's the area of the back? XH, the left side and the front side, they're all XH, right? They're all the same. So we will have 4 XH. Now, we know the surface area is 108, so we can plug that in. It is a fixed number. So what we need to do here is we need to plug this equation into this equation to get rid of one of the variables. Now, which variable can we solve this one for? We can solve for h. If you try to solve for x, you would have to do some crazy completing the square sort of stuff that would be a nightmare to do. But the h, there's only one of them. So we can solve it fairly easily. And then we could plug it in over here. So if we subtract that x squared, we got 108 minus x squared equals 4xh. Then what would I have to do? Divide by 4x. So I have got 108 minus x squared over 4x is going to equal my h. And since I have that solved for h, both of these things have to be true, so I can take this and plug it in over here for my h. And that is going to give me x squared times 108 minus x squared over 4x. So, questions up to this point? Now, in Math 3, my students can type this into, which I don't give them one quite this hard, but in Math 3, you can type this into Desmos and find a maximum point, right? But we are not allowed to type this into Desmos and find a maximum point because we are at a calculus level for this. So we need like that understanding from the calculus perspective. And that's another reason why I said, like, these problems a lot of times are hard for them to put on the exam because you also, it's going to be a lot harder to do, but you could type it into the TI-89 and find a maximum once you get it to this point, which is not calculus, so they don't necessarily want you doing that. So when they do give these problems, they have to give in like a certain way, sometimes that they will give you. So you don't see them on the exam a ton. The reason I'm spending some time on it is, number one, I think they're cool. Number two, I think that like some college professors would expect you to be able to do this and understand it from this aspect here. So, so if this is, I think, the only one I'm going to make you do entirely by hand. So for this, we need to take the derivative of v, but right now that's kind of an ugly derivative. It's going to be like a product rule with a quotient rule. So it's kind of ugly. But what we can do is we can put this over 1, and we can simplify this sum so it'll be a much easier derivative. So first of all, if I put that over 1, one of these x's can cancel with that x in the bottom, which is going to give us x over 1 times 108 minus x squared over 4. And then I could just multiply straight across. So in the top, I would have to distribute that x. So I'll have 108x minus x to the third. And this is all over 4. And then this is just divided by 4. So you can just divide both of those by 4. And 108 divided by 4 is going to be 27x. And then there's a 1 right here with that x to the third, so I could write it minus 1/4 x to the third. So we've gone from something that would have to be product rule and quotient rule to now this just is the power rule that we have here. Okay, now we have not taken a derivative, we were just simplifying so it would be easier to take a derivative. And now we do want to take the derivative. For notation purposes, since this is a v instead of a y, we're not going to call it dy dx, we're going to call it dv dx. Or you could call it v prime, would be okay as well. And so this will be 27 minus 3/4 x squared. Okay, and this one's not too bad, so this one I am going to have you do by hand as far as checking it for this by hand. So we need, once we get a derivative, we're looking for a maximum point, we need to find critical points, right? So we're going to set this equal to 0. And so we will have 27 equals 3/4 x squared. We are going to divide both sides by 3/4, but dividing by a fraction is easy as pie. We're going to flip the second and multiply. So I'm just going to multiply by 4/3 on both sides. I'll multiply by 4/3 here, which will cancel that out, and I'll multiply by 4/3 here. So that will give me, actually, this will be easier to reduce before you multiply. So a 3 and a 27 will reduce, and that's going to give me 36 equals x squared. And I will square root both sides, and I will get x equals plus or minus 6. But what does x represent in my picture? What is x? It's the length of that bottom side. Does it make any sense to have a -6 right there? It does not. So for this case, what's the smallest theoretically that that x could be? Well, 0 is the smallest it could be, right? Probably because the only thing we're getting here is 6 as our answer. That's probably going to be our answer because that's our only critical point. There is a chance sometimes that it doesn't end up being your answer. That, like, actually there's a, like, it's an extreme where either the, like, lowest possible number or the highest possible number could be it. This is probably going to be our answer, but we'll just check. We know that our length of our side cannot be any lower than 0, so I'm going to put 0 here. We got 6. We got dv dt. So if I plug in a number between 0 and 6, such as 1, because that's the easiest thing to plug in, I get 27 minus 3/4 times 1 squared, and that is just going to give me a positive number. So I'll have a positive here. And then if I pick another number above 6, like 7, if I do 27 minus 3/4 times 7 squared, I'm going to have 27 minus 3/4 times 49. I'm going to tell you I really don't like 7. Let's go back. Let's not do 7. It's not a great number because I don't know if 3/4 of 49 is bigger than 27. I'm pretty sure this is switching to a negative here, but it's not easy to do. I actually, let's go back. Like, I think 10 would be the easiest to pick because it'll be clear. And it doesn't matter whether you pick the number closest or you could pick 1,000 if you want. But if I do 10 squared, it is much easier to do this because that's 100. 3/4 of 100 is 75. 27 minus 75 is negative right there. So for this, x is going to equal 6. That will be our maximum because we are switching from positive to negative right there. So x is 6, but I need to know the height that goes with that as well, right? Because we definitely have a maximum volume at 6, but I need to know the height that goes with this as well. So what could I do? Plug it in. You can technically plug it in to any iteration of this, but this one right here where you went ahead and solved it for h is the easiest to plug it into. So if I just go over here to the side and do that, h is going to equal 108 minus 6 squared over 4 times 6, which is going to be 108 minus 36 over 24. And let's see, 108 minus 36. Right. Be 68. 72. Is that right? I think. Over 24. And that's 3. Right? So, my dimensions for this would be 6. Was this inches, feet? What was it? Inches. 6 inches by 6 inches by 3 inches. That would be the dimensions that would give you the biggest volume for this. So, like in this particular case, you might be wanting the biggest volume, with the least amount of materials, right? Because that surface area, you're having to use materials for this. Particularly if this was, you know, if it's cardboard, your materials are cheaper. But, you know, if you're doing something different here, you know, maybe this is like, yeah, tungsten steel for transporting some sort of volatile substance or something. Huh? A disease that has no cure. Yeah, then you might want to minimize your, yeah, you might want to get that one right. So anyway, that is one example. Okay, this next example is one that they give a lot. It's a purely mathematical example, but certainly you could extend this thinking, because if you were looking at like coordinate planes on like maps or something, you could extend this thinking to apply in situations, but this is pretty much a purely mathematical thing. Certainly something you might be interested in a lot of times, though, is what is the closest point. So I'm going to graph this on Desmos really quickly. No, that's not Desmos. Yes. All right, if I do y equals 4 minus x squared, it's this graph. If I do the point 0, 2. Okay, so this is what we're looking at. First of all, so like if I'm thinking about trying to do this for this problem, actually let me just, I'm going to zoom in here and I'm going to do this magic so I can write on it. Let's make it a little smaller though. Don't need that big of a graph. As audio? How? You're going to have to show me how to do that later, not right at this moment. Yeah, show me at Quiz Bowl. I need to know how to do that. All right, so here's the question that it's asking. Because this is right here on your line of symmetry, there's going to be two answers to this, right? Because now if the point was like over here, there'd be one answer, because it's closer to this side of the graph than the other. But this point is on the line of symmetry for this graph, so there's going to be two answers. The question is, which point is closest? So would it be closest to go like left or right, this direction? All right, that's like almost 3. You know, this is clearly not the answer, but to go vertical and get 1 point. That's definitely not it, because that's 4. Actually, I'm not looking at my scale very well. That's just 2 points. But this is like, you know, 1.3 or something. So definitely that's not it. But probably we're looking at some sort of point maybe here and here. But knowing exactly where that is not going to be easy to do. Right? So for this, we know for sure that this point right here is the point 0, 2. They gave us that. I'm going to put what I think to be the closest point somewhere here. I'm going to call it x, y. Okay. How do I find the distance between those 2 points right there? What? Not mean value theorem. That'd give us like the slope. What is it? Distance formula. And distance formula is not new. It's old stuff. Anybody remember distance formula? It's got a square root. No, it's quadratic formula. All right, make sure you write this one down because you'll need it for some of these problems. X1 minus X2 squared plus Y1 minus Y2 2 squared. And some iterations of this might put the y's first. They might do x2 minus x1. It really doesn't matter. It's the difference between your x's squared plus the difference between your y's squared. The reason that is because the difference between your x's is this length right here. The difference between your y's is this here. And you're basically just doing Pythagorean theorem is what's happening with distance formula. So, for this, I know 0, 2. I've got x, y. So I've got x minus 0 squared plus y minus 2 squared. But much like our last problem, I can't take the derivative of that because I've got an x and a y. And I will run into all kinds of issues if I try to do that. So I need to replace something in here so that it's all one variable. Any ideas? Yes, perfect, Liam. So 4 minus x squared equals y. It is your y coordinate right there. Whatever x you plug in is going to give you that formula. So 4 minus x squared goes right here for y. So you don't have to create the formula, it's given to you. So I'm going to get rid of that 0 because it's kind of unnecessary. I've got x squared plus 4 minus x squared minus 2 squared. And I need a derivative, so let's go ahead and simplify this because it will make it a little easier. We've got, let's see, we got 2 minus x squared squared. So if we double square that, we will get x squared plus 4 minus 4x squared plus x to the 4th. And if we combine our like terms, that gets us down to, we'll put that x to the 4th first, minus 3x squared plus 4. Actually, we're going to do most of this one by hand, too. We might not do the last step. I can't remember what this turns out like. We might be able to do the whole thing by hand. Okay, so our distance formula is the square root of this stuff. And that derivative is not going to be very easy because it's going to require chain rule, right? However, let's think about this in ways we can make this problem easier a little bit. So, if I have square root of 27 and square root of 31, which one's bigger? Okay, if I have square root of 9 and square root of 10, which one's bigger? 10, right? How do you know that without actually knowing the values? Whatever's under the square root, if it's bigger, the square root of it's going to be bigger, right? That is always true. So, do we really need to know the maximum of the square root of this, or could we just find the maximum of what's on the inside? Whenever this stuff on the inside's biggest, the square root's also going to be biggest at that point, right? So, I'm going to say that over here, if this was like free response, although again, I don't think you're going to get a lot of these on like free response questions. If the distance, or let's see, I'm going to write it this way. I'm going to call just the stuff underneath, I'm going to call it f of x equals x to the 4th minus 3x squared plus 4. So just the stuff underneath. If that function is maximized, D is maximized. Okay, so I'm going to put that statement in, and now I can just find the maximum of f of x. And whatever that is going to be where my distance is also maximized. So I don't have to deal with the square root. Now, you could do the whole thing with the square root in it. You could just find the derivative, find the maximum point. It's just a lot harder to do. And this will make it much more manageable, particularly if we're trying to do this with minimal calculator use. So f prime of x is going to be 4x to the third minus 6x. I need critical points, so I'm going to set that equal to 0. I need to factor out of x. So 4x squared minus 6 will equal 0. So I will get x equals 0. I will get 4x squared minus 6 equals 0. That'll be 4x squared equals 6. I'll divide by 4. That'll give me x squared equals 3/2. I'm going to square root both sides. So x is going to equal plus or minus the square root of 3/2. So if I put those numbers on a number line, I'm going to have, first of all, does it make sense to have negatives in this one? Think about what x is, though. X is our x coordinate. Can we have a negative x coordinate here? We can. So it is okay to have a negative in this case, because this is not our, x is not our distance, x is our x coordinate, and you can have a negative. And it would make sense on this problem that you should have a positive and a negative. So if I had to bet, like if this is multiple choice and I was running out of time, I would just pick the positive and negative square root of 3/2 and move on to the next problem without even testing it if I was running out of time, because it's probably going to be our answers. But we want to be thorough here in what we're doing. So I'm going to have negative square root of 3/2, 0, and positive square root of 3/2. And I'm going to make a chart for this. I've got x, I've got 4x squared minus 6, and then I will have f prime of x. So the row for x is just going to be negative, negative, positive, positive. Negatives, so 3/2 is 1.5, so the square root of 1.5 is going to be bigger than 1, but smaller than 2. So if I plug in like -2 right here, if I have 4 times -2 squared minus 6, when you square that -2, it's positive. 4 times 4 minus 6 is going to be 16 minus 6. I'll get a positive right there. But if I plug in like a -1, I will get 4 minus 6. I'll get a negative. Right here, I'll also get a negative. And then I will get a positive over here. And so this is going to give me negative, positive, negative, positive. And so you can see for this, you're going to have relative minimums right here. At 0, you have a relative maximum. It's a relative maximum, not an absolute, because certainly like points way down here are a lot further away, but it's a relative maximum at 0. And it does say which points on the graph. So you need to find x and y coordinates. It doesn't say just where are the x coordinates. It says the x and y coordinates. So how do we find the y coordinates that go with these 2 points? Plug it into the original. So my original was y equals 4 minus x squared. So I could do y equals 4 minus square root of 3 over 2 squared. That's going to be 4 minus 3 halves, which is going to be 8 halves minus 3 halves, which will give us 5 halves. So I'll have the point square root of 3 over 2, 5 halves, and is it going to change anything if that right there is a negative square root of 3 over 2? It won't be, because you will square it first. You got to do exponents first, which gets rid of that negative, but does not get rid of the negative right here. So they'll have the same y coordinate. It'll be negative square root of 3 over 2 and 5 halves, which should make sense if you think about what it will look like on the graph, because your 2 points that are going to be closest are going to be like at the same y value. They're going to be just same y value, different x values for that. So these two right here will be our answer. And we're going to flip over to Desmos and check and see how it looks on that, just to see if these look square root of 3 over 2. I realize you can't use this on your exam, but just to... So that point right there, that looks about right, I'd say, and put a negative right there. These 2 points are our closest points, which would have been difficult to pin down that exact value, because square root of 3 over 2 is not a simple answer, but you can find the exact value here if you need. Okay, questions? Let's see. I'm going to skip 3 for right now. Well, how much do I need to go in order? Let me look real quick at homework, because I need to make sure I do the ones that are more similar to your homework tonight first. So let me look real quick at homework, because as you can see, these questions take a little while to do, which means you won't have a ton of them for homework. It would help if I went to the right class. Let's see. Let me look real quick to help me decide on which ones to do. What I'm wanting to do is jump ahead to my favorite problem, but I don't know that the homework tonight is going to have that favorite problem on it. I might have to save it. All right, we are here. Let's see, 262. And 16's like the one we just did. Yeah, we need to do the next one. 17. 20. It's like what we did, sort of. And 33. 33 looks like. Yeah. Okay. And my favorite. We might not get to my favorite problem until tomorrow. So let's not skip 3 though. You got something similar in your homework. I want to see. All right, rectangular pages to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? So again, certainly you're probably not going to do this on a small scale, but if you are producing something and you want to use the least paper possible, but you want these things to be true, then, and you are producing it like on a mass scale where the amount of paper you're using matters versus using 1 sheet of paper at a time, you know, then it could be something that you would want to look at. So we've got a piece of paper. It is rectangular. And we know margins at the top and bottom we want to be 1.5. See, here in the middle is where we're going to actually have our print. And then on the sides, we just have a 1-inch margin. All right, and I know in the middle that I have 24 square inches of print. So whatever you're printing, you need that much space for whatever text or whatever you have there. So what I want to minimize in this case, I'm minimizing the amount of paper used. Okay, so I'm trying to think which one. So I want to minimize the area of the whole page, right? What do I know though? What area do I know? The center, right? So what I'm going to do is I'm going to call this piece right here X. And I'm going to call this piece right here Y. And I know it is a fact that X times Y has to equal 24. But what I need to know is the area of the whole page. What is the length or the width of the whole page? 24 is not the length or width. It is your area. So it could be 4 by 6 or 6 by 4 or okay. You're not going to be able to answer this with a number. What'd you say, Valerie? You're close. It is X plus 2 because you're adding 1 on either side. So this middle part right here is X, and then you're adding 1 inch to either side. So the length or the width of this paper is X plus 2. Okay. What is the height of the paper going to be? That is going to be Y plus 3 because you're beginning with Y there in the middle, and you're adding 1.5 inches on top and 1.5 inches on bottom, so that'll be Y plus 3. Now, our problem is that we have an X and a Y, and we're wanting to minimize this equation because it wants to know least amount of paper, and this equation is the one that gives us the area of all the paper that we're using. So we need to solve this for X or for Y. It does not matter which one. I'm going to solve it for Y just because I like to use X's better. So Y equals 24 over X. We are going to take that and plug it in over here for the Y. So that gives me X plus 2 times 24 over X plus 3. And I do not like, well, do I like that? Don't like it. You can distribute like it is, or you could use negative exponents right here. Let's just do like it is. Well, I don't know. What do you guys think? Negative exponents or like it is? Could go either way here. Would you think to use negative exponents at this point? Let's do it like it is. So if I do X times 24 over X, X times 24 over X, what's that going to give me? 24. Okay. Then I have to do X times 3. That's easy. Plus 3X. Then I have to do have to distribute this 2. So I got to do 2 times 24 over X. What's that going to give me? 48 over X. And then I have to do 2 times 3, which is going to give me 6. Now, definitely at this point, if you did not already, you could have already done this, you need to switch do some negative exponents. So you got 24 plus 3x plus 48x to the negative 1 plus, oh wait, put that 6 and that 24 together. So that'll be 30 right there. Okay. We need to know the minimum of this, so we're going to take the derivative. So we will get for our dA dx, or we could just call it a prime, we'll just get 3 minus 48x to the negative 2, which we probably want to call that 3 minus 48 over x squared. And so we need to know critical points. 0 is a critical point because it will give you a 0 in the denominator, and then we need to say 3 minus 48 over x squared equals 0, so that's going to be 3 equals 48 over x squared. Can't solve for an x while it's in the denominator, so I would multiply both sides by x squared. So 3x squared equals 48. And we'll divide by 3. Does that give me 16? I think. You'll also find a lot of these like textbook problems are very neatly written so that you get whole number answers. In the real world, probably would not always happen that way. So you will get plus or minus 4 for this. However, is 4 a reasonable, or negative 4 a reasonable answer for this question? It is not, because you're not going to get a negative length. So really, you just want to include 0 is the least it could be, and then you got a 4. 4 is probably your answer. If you are doing one of these problems and it's multiple choice and you're out of time, just pick 4 because it's probably your answer. But if we plug this into dA dx here, which was here, we got, like if we plug in a 1, we'd have 3 minus 48 over 1. So that's going to give me a negative. If I plug in something bigger than 4, like 10, I'm going to have 3 minus 48 over 100. That'll give me a positive. So this is, in fact, our minimum. 4 is my x. I need to find my y. So x times y equals 24. We know that. Actually, we had it solved. It doesn't, well, either way, it's, so 4 times y equals 24. Y is going to be 6. Now, 4 by 6, are those my inside dimensions or my outside dimensions? They're the inside because my x and y were labeled on the inside. What's that ask us? What should the dimensions of the page be? So we need the dimensions of the whole page, not just the inside. So if this right here is 4 and this right here is 6, what is the full height right here? 9. And what is the full width going to be? 6. So we would have a page that is 6 inches by 9 inches there. And that would be our most economical use of space if we had these conditions. Okay, I think we're going to do one more. Number 6 is my favorite problem, but we're not going to get to it till tomorrow. So I want you to. All right, let's do 4, and then we'll be done with what we're going to do today, so you guys can work on your assignment. All right, so two posts. One is 12 feet high and the other 28 feet high. Stand 30 feet apart. They are to be stayed by two wires attached to a single stake running from ground level to the top of each post. Where would the stake be placed to use the least wire? So this is sort of an oversimplified situation. However, I know one of my husband's good friends, we went to high school with him and college too. He was my husband's roommate in college. He was an engineer also. He works for companies that put up cell phone towers. So certainly, because there's a lot of engineering that has to go into this, because I did not realize this until a while back. But not all cell phone towers, certainly. But there are cell phone towers that are like taller than skyscrapers. They're really, really, really tall. So whenever you have something like that, I mean, you can imagine like trying to take a pencil and balancing it. You know, it's not going to be easy to get. That pencil's terrible. I don't think I have anything that would balance. Oh, let's see. I can get that. Like, you know, you can't do it. If you have something really tall and skinny, it's going to fall over easily, right? So because I can't even, you know, start to do that. So there is actually a lot of engineering that goes into making sure cell phone towers are sturdy enough to stand. Now, there's certainly a lot more than just this sort of like simplified version of what we're going to be looking at, because we're looking at just two post situation. But you have to, you know, usually whenever you see them, they've got those wires coming down from each side to secure them. There was a lot of math that went into figuring out where those wires need to be, what they need to be attached to, and all of those things. Now, there's a lot more that goes into it than just what we're doing here, but this is like a piece of it, right? So, yeah, my husband's roommate, he, as the engineer, had to climb them some. I don't even know what they needed him up there for, but he had to climb. He had to go places and climb them some, and they're super duper tall. Plus, they move, like they sway whenever you're up there. There's another thing you got to factor in. You got wind, so you're like up there. I'm sure that you look like it's not moving, but it probably feels like you're going back and forth. So I don't think I would want to do that. But there is now I don't know if he has to go climb towers now. That might have been something that the expendable low man on the totem pole was made to do. I'm not sure. And I know he switched companies. I think the company he works for still does the same thing, though. So, anyway, there's jobs in this out there that are slightly related to this. I'm not saying this is all of it, but slightly related. So, I'm not saying that the guys putting, like, power poles in are necessarily sitting down and working this out. But somebody somewhere has to think about this on a level. So, we got one that's 12 feet high right here, and the other is 28 feet high. So we know this is 12. We know this is 28. All right, and we know that they are 30 feet apart. So from here to here is 30 feet. Okay, so they want to attach these two poles to the same, like a wire to these two poles. And for this particular case, their only concern is using the least amount of wire. Now, in real life, there'd be a lot more concerns that you would have. Have you placed it at the right angle so that this pole's not going to fall over? Certainly, these poles are going to need like more than one wire in the other direction, those sort of things. But the only thing they care about right here is least amount of wire. So, let's talk about some options that you have, right? So, if we have this scenario, and I'm gonna lock this in place because I can do this. you don't even necessarily need to write this right here down. Write that picture, but don't do the next step I'm going to do. How do I do that? Lock in place. Okay. All right. So it is an option to put the wire. Now, it seems like this would be a really bad idea. There's an option to put the wire down here at the bottom. I'm pretty sure this is going to be ineffective. But your wire could go just like straight down the pole over here to the top of the 12-foot pole. So if you do that, the length of wire you're using right here is 28 feet, right? Plus, how could we figure out the length of this wire? I could do Pythagorean theorem. So if I do that real quick on my calculator and do square root of 12 squared plus 30 squared, I am going to get 32.311. So that would give me, if I added 28 to it, I'd get like 60. I should add that in my hand. 0.311. Right? That's an option. What other option do you have? You could go like to the tallest. You could do it this way. I don't think this is going to be very effective either, but you could. This is 12 right here. Then you could do square root of 30 squared plus 28. Oh, wait. Hold on. My calculator's not ready. Okay. 30 squared plus 28 squared is going to give me, green button enter, 41.0366. So if I add 12 to that, so this was this part right here. This one was 41.0366. And if I add those together, I get 53.0366. So if your only concern is least wire out of these two options, you would choose that second one. However, I feel like that there's probably an in-between here, right? There's probably an in-between where we got some point right here, and we're going to go like this. Probably. Now, I've got to do Pythagorean theorem with both of these, right, to find the length of both of these pieces of that wire. So I need to label something here. I know the entire length of this is 30, but I can't use that for Pythagorean theorem because it's not in the bottom of my triangle. So what I'm going to do is I'm going to call this piece right here X. If that is X, what is the other part of that? What could I label it? So if that is X, what is this red section that I've got right here? It's not going to be a number. It's going to have a... I could call it Y. I could call it Y, but then that's going to be two variables. So I'd like to use the X. It's right there for you. Yes, 30 minus X. Because they have to add up to 30, right? So if this part is X, like if I knew that was 7, I'd do 30 minus 7 to figure out what it is. Or if I knew this is 10, I'd do 30 minus 10 to figure out the other part. So it's just 30 minus X. Okay, so for this part right here, I'm going to call this A for right now. Okay? I would know that X squared plus 12 squared would equal A squared. Right? And I want to know the length of A, so I would need to square root both sides. So I'm going to get A squared, square's gone, sorry. A is going to equal square root of X squared plus 144 for that. So that is the length of that side right there. Then let's make this blue right here. And let's call this B. So for B, it's going to be a little more complicated. Right? For B, I would say B squared equals 30 minus x squared plus 28 squared. And I'm going to end up square rooting both sides of that to get the B by itself. Oh, that should be squared right there. Oh, wait. I put my square in the wrong spot is what I did right there. That square should be on the outside of the parentheses. So, no square on the inside. It goes on the outside. .28 squared is 784. And if we wanted, we could simplify this, but I'm gonna let us use a calculator on this one because it gets ugly. So those two pieces of wire, that's my total amount of wire, right? So I'm gonna write an equation for this. I'm gonna call it W for wire. You call it whatever you want. And it would be the square root of x squared plus 144 plus the square root of 30 minus x squared plus 784. Now, let me think of what I want us to do here. How much am I going to do with the calculator is the question. We're just going to do the whole thing on the calculator. I do want us to do this. I do want us to do this the calculus way. We could graph that and find this. Grab your calculator. Okay. So type that equation into your y1. So you're going to have square root. Zoom way in on that. Calculator there. So you're going to go to y equals, you're going to type this in. I'm going to just see something here. Let me just see something here. I'm going to tell you if we're going to do this. Okay. All right. I changed my mind. All right. All right. So I'm going to let you guys, on the ones I have deemed like calculator active problems, I'm going to let you guys basically just do it like we would do in Desmos, where we're going to type it in and graph it. The main thing I'm worried about is being able to set up the equation for that. We certainly could do it with a derivative. What I did just then is I typed in to take the derivative of this, and it just gets really ugly, and you could probably use a solve feature, but it will graph this for you. This is a type of problem I think is like worth looking at because it's like kind of a cool application, but it just gets a little bogged down in the details of it if you try to do all of it with calculus by hand. It's crazy to think like at one point they would have done that. But we can graph this on this calculator, so we're not going to do like we're not going to do the derivative for this. So if I go to the graph, now part of the problem is getting the window right on this. What was the like absolute most this could be? Because I did run through it at the beginning. What was the most I had for the wires? It was like 60 something, right? So let's go to back to the window, and let's go from like 0 to 60 on this, and I'm going to do zoom fit, and we'll just see if it works. I don't know if it will. The window can be very hateful on this. Desmos is so much easier. So I just went to the green button, F2. I changed my X-min to 0, X-max to 60. Okay, and I think this is going to work. It probably shows more than we really need it to, but we definitely can see where it looks like we have a minimum point for this, right? So we are looking at the graph of the amount of wire. So we don't have to take a derivative. We are looking for just that minimum point on this. So when I give you ones where I'm letting you use the calculator, it's kind of taking some of the calculus out of that, but that's all I know how to do on these. I need to work on this unit a little bit. So we want minimum. If you'll hit F5, it's third option right there. It is going to say lower bound. Whenever this calculator says lower bound, it really means left bound. Now, it's really hard to see, but whenever you hit the arrow, it will make the writing go away. So you want to go to the left side of that minimum. You'll hit enter. It's going to say upper bound. You're going to go to the right side of that minimum point and hit enter. And my minimum is at 950. So I would have that X will equal 9 feet. So my answer would need to be 9 feet from the base of the 12-foot pole. That will give you your minimum. And the amount of wire used is 50 at that point. That one can be done by hand. You get whole number answers, but it is terrible to do by hand. Okay, so your assignment that you are going to have tonight, that let's try to at least get maybe the first one set up, is going to be page 262. You're going to have 16, 17, 20, and 33. So you just got 4 problems for these. These take a little while to think about. And let me look and see which ones I'm going to let you use the calculator on. 16 and 17 should definitely be ones. Any of these, I do not mind if you use the calculator for just simple addition, subtraction, multiplication, division, square roots, that sort of stuff, right? So if you're having to plug in numbers that are a little bit large, I am okay with you guys doing just the arithmetic with the calculator. But the derivative and all of that stuff, I want done by hand on 16 and 17. 20. I want also for 20, I want you to do the derivative by hand on that. Now your surface area is 337.5, so it's fine to use the calculator within the problem to add, subtract, multiply, divide. But for the first 3, I want you doing the calculus by hand. I want all those done with calculus. But for 33, this one is totally calculator active. More than just adding, subtracting, multiplying, dividing. So for 33, once you get that one set up, you can use the calculator to find the maximum or the minimum for that. I will definitely be here in the morning if you need help with these. For each of these, try to set up an equation, right? If you're stuck, try to set up an equation. We have done ones very similar to the first three. The third one's going to be a little bit more of a challenge for that. Also, if you need any formulas for things like volume of a cylinder or volume of a sphere or surface area of a sphere, if you look in the back cover of your book, all of those formulas are there. And if you see something like a right circular cone, it's just a regular cone. Right? If you see a right circular cylinder, it's just a regular cylinder for those. So those are all in the back of the book if you end up needing them, particularly for 33. You might need